I was hiking last weekend, through this really dense old growth forest.
Hmm.
And I had that thought. I looked down at the roots and the moss and I wondered if the trees were talking about me.
Right.
We've all seen the articles about the Wood Wide Web, right? This idea that they're gossiping, sharing secrets. It's a very romantic notion.
It is. It's a beautiful image.
Mm.
And it really captures the public imagination because, we love to find human-like traits in nature.
Exactly.
But if we peel back the poetry and look at the actual biology,
Hmm.
the reality is uh, less like the movie Avatar and maybe more like a bustling, sometimes ruthless subterranean stock market.
Okay, so let's separate the Hollywood script from the science. These networks, these common mycorrhizal networks, what does the actual hardware look like?
So at the foundation, we are basically dealing with fungi. These are incredibly long microscopic threads called hyphae.
Hyphae, right.
And they physically connect the roots of at least two different plants. And look, this isn't rare. We're talking 80, maybe 90% of all land plants form these connections. It's the rule, not the exception.
So the entire forest floor is just wired by default.
Essentially, yes.
Yeah.
But the interface, that's where the real engineering happens. Depending on the fungus, you get different kinds of connection ports.
Ports.
Yeah, you might see a Hardig net, which is like a mesh glove wrapping around the outside of the root cells. Or you get arbuscules, which are these amazing tree-like structures that actually penetrate inside the plant cells themselves.
Whoa, hang on. They go inside. That sounds less like a connection and more like an invasion.
A consensual one.
Yeah.
Those arbuscules are the trading floors. That is precisely where the fungus hands over things like phosphorus and nitrogen, and the plant pays for it all with sugar.
Okay, so a trade happens. But the gossip, the language, I've read about electrical signals. Is that what we're talking about?
Fungi do show electrical activity. We call them action potential-like events.
That sounds like a nerve impulse.
It does, but here's the catch: the timing. These signals move at a snail's pace. We're talking maybe 0.5 to 10 millimeters per second.
Wait, okay, let me do the math here. At that speed, if a beetle starts chewing on one tree and it tries to warn a neighbor, say 10 meters away, that message would take hours, maybe days to get there.
Exactly. By the time the warning arrived, the damage is long done.
Mm.
So while the machinery sort of exists, there's no real evidence that they encode specific messages like herbivore attack. It's probably more a reflection of their metabolic state.
So less of a chat room
Right.
and more like a shared, slow-moving circulatory system, a kind of decentralized intelligence. And, speaking of optimizing decentralized systems,
I see the connection coming.
you know it. This deep dive is sponsored by Embersilk. If you're trying to structure your own intelligence networks, whether that's AI training, automation, or software integration, you really can't rely on slow signals. Embersilk helps you uncover where agents can make the most immediate impact. It's all about building a smarter ecosystem for your business or your life. Check them out at embersilk.com.
Which brings us right back to the ecosystem of the forest. And we have to talk about the biggest controversy in the field right now,
The mother tree.
the mother tree.
The Suzanne Simard hypothesis, yeah. The idea that big old trees are altruistically feeding the seedlings, helping them out.
It's the narrative everyone loves.
Yeah.
But this is where the science gets messy and honestly really exciting. There's a huge debate between Simard's camp and skeptics like Karst and Henriksen.
So what do we actually know?
We know for a fact that carbon, nitrogen, and phosphorus do move between plants through the network. That happens.
But is it enough to actually matter? Is it a lifeline or just leakage?
That is the million-dollar question. The skeptics point out that the amount transferred is often tiny. We're talking low single-digit percentages. And sometimes it might just be simple diffusion through the soil, not a targeted delivery.
So it might not be charity. It could be an accident.
Or it could be piracy.
Piracy.
Yeah, think about mycoheterotrophic plants. Certain orchids, for example. They don't photosynthesize. They literally hack into the network and steal carbon from other trees. They give nothing back.
So they're not singing Kumbaya. They are hacking the mainframe and siphoning off funds.
Exactly. But here's the optimistic twist in all this. Even if it's a market full of traders and pirates instead of a loving family, the network itself creates incredible stability.
How so?
It buffers the whole forest against stress, like a drought. The sheer redundancy of connections means that if one part of the system fails, the whole thing doesn't collapse.
I love that. So the resilience doesn't come from altruism necessarily, but from the sheer complexity of the infrastructure.
It connects everything into a resilient whole.
That leaves us with a lot to think about. So next time you're walking in the woods and you think about this network, maybe ask yourself this. If the forest is a market, not a family. What's the price of entry for a new seedling trying to plug in?
A fascinating question.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.